Welcome back to compiler construction. So after we took a closer look at specific problems of bottom-up parsing and look at details of implementing a parser using the YAC parser generator, now let's take a look at additional problems that show up. So in our last lecture, we've already seen that some errors in our program cannot actually be detected by a scanner and parser alone. So we need to do additional steps in order to actually detect and print out information about these errors to the programmer trying to use our compiler. So first we'll take a quick overview to see where are we standing now. So of course you've seen we are developing our compiler more or less from front to back. So which steps have we already more or less completed or talked about? Which steps do we need to take next? And then we'll talk about this more to languages thing than the context-free grammars can actually describe. So we're taking the step going from syntax of a language to the semantics, so the meaning of a language or a program expressed in that language. And for this, we'll introduce syntax-directed translation. First, an ad hoc impromptu approach. We'll talk about some examples for this. And finally, at the end of this lecture, we'll present a tiny, but of course very imperfect, arithmetical expression compiler that actually manages to translate arithmetical expressions to ARM assembly language. So let's go back to this diagram you've seen a number of times already. So here are again all the steps our compiler has to take in order to translate our source code to some, for example, machine language program. So we've talked about lexical analysis and syntax analysis in detail. So we know that in a real compiler, these two actually interact by permanently exchanging information about the token that's passed and so on. So essentially, we can still look at it in a simplified way and say the lexical analysis just provides us with a token sequence, and the syntax analysis finally builds a syntax tree. So our next step to perform would be to perform semantic analysis. So syntax analysis has used all these grammars, and we had this syntax tree, which actually links these annotated tokens together. So for an expression, we have this token equals, and we know it's of token type operator, or we have this token X, which we know it is of a token type ID. So the task of semantic analysis now is to go through our syntax tree and check a number of things. So the first thing it needs to check is name analysis. So if we're using the name of a function or a variable in our programming language, has this actually been declared somewhere, or are we trying to use something that has a name which is not declared anywhere else in the program? If there's an existing declaration, is it actually correct? So are we in the correct scope, or was this variable just declared in a completely different function here? Then when we do expressions and operations on names or variables, we need to perform type analysis. So we need to check if it is possible to obtain a correct result, so to check for the correct type of expressions, if they're compatible with each other. And finally, of course, we need to create so-called symbol tables to do this. So symbol tables are tables that actually map an identifier to all this meta information we want to provide about it. So its type, its position in the source code, and so on. So which errors can there be that are not detectable by the scanning and parsing approaches that we've seen? So consider the C program we're showing below, and try to find out which errors can you actually detect here, and which of these errors could you actually detect using a context-free grammar. So what we have here is a function b, which is declared using a number of integer parameters, and we don't really care what this function is doing at the moment. And we have another function foo, which declares a number of local variables here. Then it calls our function bar, does some calculations on our local variables, prints something, sets another local variable to a value, and finally returns. So let's go through this step by step to see what's wrong with this program. So first, we might figure out, oh yeah, there's a call to b somewhere here, and this call to b has 5 parameters. But wait, b was declared Well, to only accept 4 parameters. So that's a wrong number of arguments to bar. That's very difficult already to detect for a parser, because a parser would need to remember how many arguments a bar would actually take. All right, what's the next one? Well, in this line below here, we access element number 17 of an array G, but up here, G was declared to only contain 0, so 1 element, essentially. So essentially, we would try to access an element of an array that's beyond the array's limit. Next thing, again, calling the function bar. So it's not only that we have a incorrect number of arguments, but if we check bar, we see, okay, the first parameter we pass is an int. That fits, would be passed as a here. The second one is, again, an int. I would be passed as b. The third one is, oops, a string. So a string is passed as a pointer to the start of the string, like it's common for character arrays in C. So it means we would try to pass a character pointer here, but our function b would actually expect an integer. So that doesn't really work. So ab, this string, is not an integer. What else is there? Well, down here, we're trying to calculate some value using f. But f, well, is the name of an array. So essentially a pointer to the start of the array and not an element of the array, which would be a correct integer value for our expression here. So there's a wrong or non-existing dimension when using this array f here. That also doesn't work. Finally, in printf, we're trying to use an undeclared variable q here, so this can't be found anywhere else, and, well, assume it wasn't declared as a global variable here. And is that all? Oh, there's something else. So in this last line of code, we try to assign the integer number 10 to p, but up here, p is a character pointer, so we just tried to just assign a integer value to a character string, which also obviously has some problems. So all these errors actually affect an area that's beyond syntax in our compiler here. So these errors are what we can call deeper than syntax. So we know that there is a level of program correctness that is deeper than our grammar. And in order to actually generate working code, we need to understand the meaning of this. So to generate code, the compiler needs to answer quite a large number of questions. So questions like, if we have a name x here, is this name x actually indicating that the related variable is a scalar value or an array or a function? And is this x actually declared at all? Are there any names that are not declared or names that are declared but not used? That might not be a big problem, but it usually is an indication that the programmer forgot something. So that's why your compiler warns about this. If we have a reference to a name x, which of the declarations of x is the correct one to use in the given line, in the given context? If we have an expression here like x times y plus z, is this type consistent? So can we actually calculate something? So if one of these would be a character pointer and the other one would be integers, well, that would be problematic. If we have an array access here, a of I, j, k, does this array a actually have all these 3 dimensions? But we also need to answer questions like, if we have something like a variable z, where can this be stored? Can this be in a CPU register? Is this a local variable on the stack? Is this a global variable in our data section? Is this maybe on the heap? Or is this some static variable that has to get some special treatment? If we have expressions like f equals 15, how should we represent this 15? So if f would be a float variable, this 15 would have to be expressed as a floating point constant instead of an integer constant. And many more things, like how many arguments does a function bar take? What's with printf that can take an arbitrary number of arguments? If we have something like a dereference of a pointer, does this reference the result of a memory allocation malloc call? If we have two pointers P and Q, do they actually refer to the same memory location? Or is something actually defined before it is used? So there's so many details, and all of these details here are beyond the expressive power of a context-free grammar. So we need to do additional steps in addition to scanning and parsing in order to actually answer all these questions. So all these questions are actually part of what we call the context-sensitive analysis. And the answers to these questions depend on values and not parts of our language described in a grammar. And well, context-sensitive analysis questions and answers involve non-local information, so it can be information stored somewhere else in our program or even outside of our current compiled file, because we might have unreferenced variables that might be only resolved by a linker. And answers may involve computing things. So how can we actually answer these questions? Well, there's two approaches here. First, we could use formal methods. There are things like context-sensitive grammars, which are more complex again, so they're in a different class of our Chomsky hierarchy. There's also things like attribute grammars. So an attribute grammar would actually be a grammar of the attributes, but there are also attributed grammars, so we could add something to our existing grammar to encapsulate and provide the attributes to our compiler. And the other approach, not using formal methods, is using ad hoc techniques. We could introduce something like a symbol table, so we could actually record information about every symbol that shows up as soon as it's declared. And then we could use ad hoc code action routines in order to actually check this symbol table information as soon as our parser encounters a use of a certain symbol here. And for parsing and scanning, you've seen formal approaches have won because they're easy to use, because you can just build like a scanner using a DFA, or you could use top-down or bottom-up approaches essentially very easily to do this. For context-sensitive analysis, mostly still ad hoc techniques are used in practice, because the other approaches here, like building context-sensitive grammars and so on, are much more complicated to get right. So for ad hoc analysis, the idea behind this is to track the definitions of symbols in a global structure, which is available to all parts of our compiler. So let's say we have this excerpt of a program here. So somewhere up here, we have a declaration of an int variable x, then we have a declaration of a float variable y, and further down in our program we have an expression that uses x, calculates 2.0, which is a floating point constant, times x, adds something which is q, which we don't know anything about here maybe, and assigns this value to our float variable y. So let's assume this program excerpt is syntactically correct. Which are the non-syntactical questions a compiler would actually have to consider when it's parsing and trying to compile this line 142 here? So of course, first our compiler would need to figure out, are all these symbols here, which we use in this expression, actually defined in our current scope? So if not, well, we have a problem, because then we don't know which value to access for something, like maybe this q here. The next question, to actually generate code later on, where are x, y, and q actually stored in memory? Because for efficiently calculating an expression, the CPU in your computer would need to load the value of x into a register, the value of q into a register. Well, do this calculation on these values in registers, and finally store the register result back into memory at the location of y. And finally, we need to figure out if the types of x, y, and q are compatible with each other. So we've seen already if one of these would be, for example, a character pointer, and that's a bit difficult to handle. Well, but still, there might be ways if the types would be incompatible, like we have here. We have an integer we multiply with a floating point constant. In this case, the types could be made compatible, for example, by using implicit typecasts. So we could actually do a typecast, so a propagation of a value by changing its representation from the integer representation of 2 to a floating point representation, then do a floating point multiplication here to obtain 2.0 times x as a result. And finally, we would need some floating point value for the whole expression here to be able to successfully assign this to our variable y. So if we have this expression here and the rest of the code with our declarations, we can have a simplified abstract syntax tree like this. So for each declaration, we have that one here. So that would be the first one, declaration, which has a type of an integer on the left-hand side and our name x on the right-hand side. And then we have, well, lots of other things in our syntax tree. And so finally, we have an expression that says, okay, it's an assignment here. We assign to our variable y, which is an identifier or name, well, the assignment operator here, and then there's an expression, and this expression has been evaluated according to arithmetic precedence rules. So first we evaluate our multiplication here, 2.0 times x, and then the sub-result of this first part here of our expression is then added using the upper expression here to a variable q, and finally this is assigned to y. And the question is traversing the abstract syntax tree to answer all these questions we have here actually a good idea? Because when we encounter this x here, we need to travel all the way up here through whatever arbitrary stuff lies here to finally find our declaration of x as an integer further up somewhere completely different in our abstract syntax tree. So maybe there should be another way to do it. So this other way to do this is to introduce symbol tables. So we need to ask ourselves which information is actually required to compile an instruction. Let's take a look at that example here. We have a declaration of an int variable x here, and further down we have an arithmetic expression that actually just adds 1 to x and assigns the result back to x. So how could we actually translate this line? Well, first we have to read a value from the memory location of x. This is our reference to x here, where we read its value. Then we have to emit code to add an integer with the value of 1 to this intermediate result. So we have the result of our right-hand side expression here. And so finally we need to implement this assignment here. And this assignment means we need to store the result of our right-hand side expression into memory at the location of whatever is here on the left-hand side. So this is x again. So we need to store the value of x plus 1 to our memory location where x is actually stored. And it's very convenient to store all this information actually in a table and then provide links inside of the AST. So essentially to provide meta information to a node of the AST, and these links then link to the specific information about this variable we've just we're just trying to use here in our expression. So we have this abstract syntax tree here again. So our excerpt here for our expression in line 99, and whenever our parser encounters something like an integer declaration, well, it should add an entry to our symbol table here that we have a name x and it's of type int, and maybe if it's a global variable, we can also store its location here, like here it's an absolute location. And whenever we then compile our line 99 here, for every occurrence of our x, well, we can check our symbol table. So our expression here would first check our symbol table here to see, is there actually an x? Yes, there is. Does the expression work? So here is a +1. So something +1 is an addition of an integer 1 to something else, which should also be an integer, so name of x. The x should also be an int. Well, it is an int, and we need to load x here, so we need to check its location here. So we have a location for x, so it's 2048. So we can load something from this memory location. We know it's an integer, so we know we can add the constant 1 to it. And finally, we need to store x again. So when x shows up here again on the left-hand side of our assignment, we again need to check for type compatibility, even though it's obvious in this case, but it could be some other variable here on the left-hand side. So we need to check that the expression on the right-hand side is compatible with what we're going to assign it to. It's again an integer, obviously, and we need to store this somewhere. So we already have the location 2048. So our compiler would be happy. Now, one problem that shows up when we try to implement symbol tables is that this linking of information from the abstract syntax tree to our symbol table requires to find the table entry of X every time that name is used. So we've seen it had already to be looked up twice in our previous expression here. From the scanner, we only get the name and the information about the token type, obviously. So this is essentially a text search problem. So we need to look in a potentially large table that has like thousands of identifiers or thousands of names. And we need to look up our definition and meta information of X every time when we compile a program, every time when X shows up. Now that's unavoidable, but actually we could try to optimize this. So there are some possible approaches. First would be to use direct indexing. So we could keep a table, again, where the index is a function of the text. But this means we would limit the number of identifiers to the size of a symbol table. So when you would use more identifiers than fit in your symbol table, your compiler would complain. So for real-world compilers, that's probably not a good idea. You could also use a linked list. This would mean you keep a dynamic list and go through it and compare, but then again, the further your identifier is back in the list, because you have to start from the beginning of a list and then walk through all the pointers in your list, the more expensive the search for identifiers actually gets. So your compiler gets slower and slower the more identifiers you declare in your program. So it's probably also not a good idea. And one approach to solve this problem you've probably seen before already is to use a so-called hash table. So hash tables are a very common approach to implement symbol tables. What hash tables do is they try to convert whatever comes into as our parameter to a hash function into a number here. So for example, we have a number of slots here, which are, well, unique. So identified 0, 1, 2, and 3 here as a hash value here. And we have a unique hash function that actually always returns the same number for the same name here. So essentially what we do here is we have an unpredictable fixed length code, this hash value, and this can be computed for any length of identifiers. So this could also be a very long variable name. And the problem obviously that shows up is that, well, if you have 4 entries and like 5 different names, obviously you have a collision here because your hash function would return the same hash number for like X and maybe another name Y. And if both would refer to hash index 2, well, we wouldn't know which information to access. So in our hash table, actually these hash indices only are starts of linked lists. So that's essentially where we optimize compared to linked lists. We split up the linked list search space here. And for example, we now only have to go through a partial linked list instead of the complete linked list for all of our names in our program to find information about X. So we call hash of X, I return to 2. We know this element 2 of our hash table is then the element we have to start our search, and then we have to walk the pointers in this linked list that starts at our hash table element 2 to find the entry that actually refers to X. If we actually arrived at this final entry here and we have no more entries and we haven't found X, that would be an indication that there is no information about X. So maybe when somebody tried to use X and it wasn't there, well, we should print an error. And attached to this information on X is, of course, the information we've seen before, so about X's type, about X's location, and further additional information the compiler would want to use. So hash tables are a good compromise to use for symbol tables because they can dynamically grow with the number of stored elements. We need a constant time to find the right list to search, but of course then the time for traversing this list can be variable still. But if the hashing function distributes elements evenly, so that's a property of a good hashing function, the search time is divided by the number of lists at least. And of course you can have more than these 4 elements that we've shown. And hash tables provide us with a good balance between a static size limitation and a list length, and this can be adjusted depending on the data to be stored. Now, unfortunately, there is no implementation of hash tables that's directly available in C. We've already discussed about why should we use C for implementing compilers, and this is one disadvantage of using C because C doesn't have these higher level data structure or type abstractions for something like hash tables, which actually means that we would have to implement this on our own.